Okay. We have discussed a single qubit gates. Some of the single qubit gates, those are the X gate, Y gate, Z gate. Of course, out of them only, there are some more, as I mentioned in the previous video. That is the Hadamard gate. There is the Hadamard gate or the H gate, the S gate. Of course, again, the T gate, about which we have discussed in the previous video, and also have found out the eigenvalues and eigenvectors. Okay, so Hadamard gate is denoted by H. It is something like this. H is equal to 1 by root 2, 1, 1 is the first column, 1 minus 1 is the second column. Actually, Hadamard gate is the best example to create superposition. Is a best example to create superposition state. Superposition state. Okay. So H when applied on ket 0 would give me something like 1 by root 2 ket 0 plus ket 1. This is equal to ket plus. And then H when applied on ket 1, 1 by root 2 ket 0 minus ket 1 gives me ket minus negative. Okay, actually ket plus ket minus are eigenstates. There are these Bell states, there are these eigenstates. Again, when needed, I will talk in detail about that. Okay, so Hadamard gate satisfies certain properties. H is equal to H cross means what? It is Hermitian. A matrix is equal to its conjugate transpose, implies that that matrix is Hermitian. Okay, of course, all the values are real, so I can just say transpose only instead of conjugate transpose. And then H is equal to H inverse also. You can check once. H is equal to H inverse, which implies that H is orthogonal or unitary kind. Also, H square is equal to I. Okay. All this we will check, but then the reason behind why I have chosen Hadamard gate is there are certain things that can be done with the Hadamard gate. Okay, which I would like to just I would like you to just focus on. Okay, there is one proof. I mean, you need to check what the value of H U naught H. H is the Hadamard gate, U naught is the X gate. So pre-multiplication and post-multiplication gives what is I need to check. 1 by root 2 is Hadamard gate. 1, 1, 1 minus 1. U naught is my X gate. So 0, 1, 1, 0. Okay, of course, 1 by root 2 is again there. 1, 1, 1 minus 1. 1 by root 2 into 1 by root 2 would be 1 by 2. Okay. Either ways I can do. First, I will go with multiplication of this 2 and get back to 1, 1, 1 minus 1. 0 into 1, 1 into 1. 0 into 1, 1 into minus 1. 1 into 1, 0 into 1. 1 into 1, 0 into minus 1. So this gives me this. And then finally, 1 into 1 plus 1 into 1 would give me 2. Okay, 1 into minus 1 plus 1 into 1 would give me 0. 1 into 1 plus 1 into minus 1, this also is 0. 1 into minus 1, 1 into minus 1, minus 1 into minus 1 into 1 would give me minus 1 minus 1, which is minus 2. If I take the 2 inside, I'll be having 1, 0. 0 minus 1. You can clearly see that this is your Z gate. Okay. This is one proof that you need to check regarding Hadamard gate. There is one more interesting thing about Hadamard gate, that is H into Ketzai. H into Ketzai. What would be the value of it? I need to check. Okay. Of course, here I have checked the H into Ket 0, H into Ket 1 and all that. Okay, so what would be H into Ket 0? H into Ket Xi. Ket Xi would be alpha into Ket 0 plus beta into Ket 1. Okay, alpha is a constant. So using linearity, I can take alpha out. H into Ket 0 plus beta is also a constant, H into Ket 1. Okay, so H into Ket 0, that has given me the state. Of course, eigenstates are there, but anyways, 1 by root 2 Ket 0 plus Ket 1. Of course, alpha is there here. Beta by root 2 Ket 0 minus Ket 1. Okay. So Ket 0s and Ket 1s, if I join together, beta plus 1 under root Ket 0 plus alpha plus beta by root 2. Okay. Alpha minus beta by root 2 Ket 1. Okay. There's one more proof, that is H square is equal to I. This also I can check. H squared. H squared first I will find out. H squared is H into H, which is 1 by 2 into 1, 1, 1 minus 1, 1, 1, 1 minus 1. I multiply, so I'll be having 2, 0, 0, 2. Taking 2 inside, I'll be having I. Okay. Now, H squared into Ket Xi. So I multiply Ket Xi on both sides. H squared is nothing but 1, 0, 0, 1 into Ket Xi alpha beta is what I have, which is nothing but alpha beta. Okay, which is nothing but my Ket Xi. Okay. Of course, this would give me I, and this is nothing but my Ket Xi. Okay, hence I can say H squared is equal to I, or H squared Ket Xi is equal to Ket Xi. Okay, this is how I will prove. This is an interesting result to be noted. Okay, apart from this, I'm talking about gates. Okay, there are also the S gate and different things. Okay, I will talk about them later, but I'll try to just show things like 3 qubit gates. 2 qubit gates, enough number of things we have done. Of course, some more things can be done a little later, probably in the next video. Now I would like to I would like to bring to your notice the 3 qubit gates. Okay, or the multiple qubit gates. Usually for that I'll be using this controlled gates. The things that I have in quantum are controlled gates. These gates operate on multi-qubits, where one or more qubits act as controls that determine whether the gate operation is applied to the target qubits. Okay, now first and foremost 2 qubit gate is my C naught gate. Okay, there are a list of things. Let me write here. C naught, CZ gate is there. CS gate is also there. Okay. Yeah. If anything else, I will let you know. But then what is the thing about C naught? I know that NOT gate is my X gate. So first I will write so that remaining things follow. C naught gate, it is in short, it is I 0 0 X. X is called my NOT, right? NOT gate. So If I rewrite it in matrix format, it is 1 0 0 1. Null matrix is 0 0 0 0 0 0 0. X gate is 0 1 1 0. Okay, this is my C naught gate. What happened if you see here? Whenever the target, see, the interesting thing about C naught gate is, if the control bit is, as long as the control bit is 0, nothing happens, no change. But if the control bit is 1, the target flips from 1 to 0, 1 flips from ket 1, flips to ket 0, and ket 0 flips to ket 1. Okay, that's what I can see in the last thing. Okay, I can just write here, see, 0 0, where this is the control. This is the control bit and this is the target bit. Okay. So when, as long as control bit is 0, I will get the same thing. Yeah. Okay. As long as the control bit is 0, I'll get the same thing. Yeah. Okay. Now, once the control bit is shifting to 1, what is happening? Target bit is also shifting to, 0 is shifting to 1. Okay. The control bit is 1 only. 1 is shifting to 0. Okay, this is how this gate works. Okay, this is how you should give the explanation of C naught gate. Okay, next what I have is my CZ gate. Once you got the hint for not C naught, I think you can give a guess for CZ gate as well. CZ gate is nothing but I, null matrices Z. Okay, if I reread the full expansion, then it is like 1 0 0 1 0 0 0 0 0 0 0 0. My Z is no flip in the state, flip in the face. Okay, so this is my Z, CZ gate. What is the best thing? One more 2-qubit gate. This is another 2-qubit gate. What is the thing that I observe? See here, what I have observed here when once I have written, there is a change in this two. Okay, first two are proper only. Second two, there is a flip. Okay, now if you look at this, accordingly you can write. What that is 0 0. If I have 0 0, then it is 0 0 only, no change. When I have 0 1 also, no change, 0 1 only. When I have 1 0, what has happened? 1 0 also, there is no change, by the way. 1 0 also, it is 1 0 only. Now when it comes to 1 1, when the control bit is 1 and the target bit is 1, there is a flip in the phase, not in the state. What has happened? Actually, it has to be 1. The last element has to be 1, but it has become -1. So what does CZ gate do? Let me write the properties. When control bit is 0, nothing changes. Nothing changes. Okay. When control bit is 1 and also target bit is 1, then what happens? Change in phase happens when they are passed through the CZ gate. Okay, with the same flow, let us go to CS gate. CS gate. Okay, yeah, I was making a mention of CS gate in my previous video. What is CS gate? Okay, coming to CS gate, as a S gate would be what? Square root of Z gate, right? So Z gate is 1, 0, 0 minus 1. Under root of 1 is 1 only. 0 is 0. Under root of minus 1 would be I. Okay. So CS gate is formed with the S gate. So with the previous idea, I am writing the CS gate 1, 0, 0, I. Okay. Yeah. So what has happened in CS gate is, of course, I can draw the pic like this. Okay, what has happened? When the control bit and the targeted bit both are 0, no change. I can see 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0. Okay. So no change. When the control bit is 0, there is no change, obviously. When the control bit is 1, also there is no change. Yeah. When the both control and target bit both are 1, then there is a phase flip. Okay. So both control and target bit are 1. There is a change. There is a phase flip. Okay. Right. These are some of the examples. Of course, along with this, there is this swap gate, which is again a, oh, 1 second, swap gate. Swap gate, which is again a 2 qubit gate. Okay. Of course, usually swap gate is called as a reversible gate. It is a reversible gate. Okay, I can just draw. It's a reversible gate. Okay, I'll just give you the truth table for it. What happens is when ket A passes through the gate, I get ket B. When ket B passes through the gate, I get ket A. Okay, I can just give you the truth table as well. A, B, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so what happens is, no change. Swap, 0 becomes 1, 1 becomes 0. 1 becomes 0, 0 becomes 1. Okay, and then there is no change. Right, these are some of the examples of 2 qubit gates. Of course, I can also talk about 3 qubit gates where there are two CC naught gate, okay, or Toffoli gate, where the CC, two controls are there, where there are two controls, CC naught. Okay, I will just write for example, that's it, a CC naught gate, I 4 by 4, null matrix 4 by 4. It's nothing but formed with C naught gate, guys. Why I'm writing 4 by 4, you understand. C naught gate is a 4 by 4 matrix. So remaining also should follow the same format. Okay. C naught gate is a 4 by 4 gate. Hence, of course, here there are two targets. I mean, two controls are there. So accordingly, things will happen. Okay, I think I made you clear regarding 2-qubit gates. Of course, initially we were aware of 2-qubit gates. Now I have made an explanation to 3-qubit gates as well. Okay. Thank you.